If you've been following the AI space, for the last couple of years, you've definitely heard the phrase, the chat GPT moment.
Oh, yeah, constantly.
It's that leap from models that just organize information to models that can actually reason and converse. But what happens when that moment, leaves the screen and gets behind the wheel of a 2-ton vehicle?
Well, that is the crux of this massive shift happening right now in autonomous vehicles.
A move away from systems that just perceive and react?
To systems that can genuinely reason about the world around them. And, crucially, explain their choices.
And that's the core of the source material we've put together for you today, right?
Exactly. We're diving into a whole collection of research announcements and technical blogs that detail NVIDIA's new Alpamayo family. And this isn't just a new chip or it's a slightly better sensor.
No, it's a whole ecosystem.
It's a fully integrated open source ecosystem. You've got the models, the data, the simulation tools, all of it designed to build what they're calling thinking autonomous systems. Systems capable of true level 4 autonomy.
The technical literature here is, it's dense. It goes into everything from transformer models to microservice simulation architectures.
It is. So our mission for this deep dive is to sort of unpack the 3 big pillars of this Alpamayo ecosystem.
That would be the model, the data, and the simulation.
Right. And explain why this kind of open tool chain approach is, well, it's fundamentally changing the race for safe level 4 autonomy. The focus for everyone now has just irrevocably shifted to generalization and trust.
Because if level 4 is the goal, unsupervised autonomy in certain conditions, the system has to handle not just the normal stuff, but the completely unexpected.
The utterly unexpected, exactly.
Okay, so let's unpack that. Specifically, how is this new VLA model architecture designed to solve that notorious long tail problem?
Oh, the long tail. It's the biggest technical barrier left. It's all those rare, complex, sometimes just bizarre edge cases that happen, maybe once every million miles.
So you're talking about a double-parked delivery truck in the pouring rain, or some weird construction sign combined with an emergency vehicle.
Things you just can't pre-program rules for. They demand something like human judgment, common sense.
And the traditional AV systems, the ones that split everything up into perception, prediction, planning, they really struggle there because they don't have the semantic context, right?
That's it. They see objects and they see distances, but they don't understand the intent behind the scenes.
So they fail.
They fail in the long tail because they treat these events as like a totally new input. And without the ability to reason about cause and effect, they either make an unsafe choice or they just become overly cautious. They freeze up.
So if a system has only seen traffic cones on the shoulder and suddenly they're in the middle of the lane, it has no idea what that means.
None. It needs to process the meaning, not just the location.
Okay, so the architectural shift here is fundamental. This is where we go from those older systems to this idea of vision language action, VLA models. This is the reasoning layer.
Yes. Alpamayo is a VLA model family that uses what's called chain of thought reasoning to inject that human-like thinking into the decision-making.
It thinks in steps.
It thinks in steps. It processes the visual input and then generates an intermediate logical reason before it picks an action. And that language part is so critical because it gives the model this abstract space, semantics, to solve problems that raw sensor data just can't.
So the car isn't just driving better, it's driving knowingly. And the promise there is huge. It's not just performance, it's explainability.
Which you absolutely need for safety validation, for regulatory approval, and, for public trust.
Let's get into the specifics of Pillar 1 then. The reasoning brain, Alpamayo 1. It's a 10 billion parameter VLA model. That parameter count alone tells you this thing is built for serious complexity. What are the specific outputs?
It's engineered to generate 2 things at the same time from all that fused sensor input video, LiDAR, radar, all of it. Okay. First, you get the precise driving trajectory, the steering, the braking, acceleration. But second, and this is really the game changer, it generates a reasoning trace.
And that reasoning trace, is it just a line of text or is it something more, like an auditable log?
It's the latter. It's a human-readable logic trail that explains why the vehicle chose that path. It turns the infamous black box into, a transparent box.
So the example they use is pretty specific.
It is. The output isn't just move left. It's the full thought. Nudge to the left to increase clearance from the construction cones encroaching into the lane, prioritizing safety over immediate speed.
So an engineer or a regulator can actually see the car's internal logic.
They can. which is incredible.
But here's where it gets really interesting for me, because 10 billion parameters, that takes monumental compute. This model isn't designed to run directly in your car today, is it?
No, absolutely not. And that's the key strategic choice here. Alpamayo 1 is positioned as a large-scale teacher model.
A teacher model.
It does the heavy lifting, the high-level reasoning during the development and training process. It provides that really strong reasoned foundation for what the correct action should be.
So how do you get that enormous, power-hungry brain into the small, efficient computer that's actually, inside the vehicle?
That's where the toolchain comes in. Developers use techniques like model distillation, quantization, and pruning.
Okay.
You use the reasoning power of that massive teacher model to train a much, much smaller, more efficient student model. The student learns the reasoning patterns without needing the immense size.
So you're basically transferring the knowledge.
You're distilling the knowledge into a highly optimized format that can run efficiently in the car in real time. It just massively speeds up development because you're not starting from scratch. And you still have that auditable reasoning.
That makes perfect sense. So the model is the brain, but a brain needs fuel, especially if you're trying to solve the long tail. So let's move to pillar 2, the data. The physical AI open data sets.
Right, and this is the fuel for generalization. The scale and diversity they've detailed it's just staggering. We're talking about over 1,700 hours of multi-sensor driving data.
Specifically, 1,727 hours, right? Something like 100 terabytes.
That's it. But the big numbers are impressive, but it's the diversity that's really the story here.
The geographic spread.
The geographic spread is the whole point. This data was collected across 25 countries and over 2,500 cities. I mean, just think about the implication of that.
Well, a model trained only in, say, California knows one kind of stop sign, one kind of lane marking.
Exactly. This model has to learn to generalize across non-standard signs, European roundabouts, different driving cultures, everything.
That sounds like a logistical nightmare to label and curate, all that regional nuance.
Oh, it's immensely difficult. You're not just labeling pedestrian. You have to label regional driving behaviors. The strategic part is that by making this globally diverse multi-sensor data open, and its full 360-degree coverage from cameras, LiDAR, radar, they're trying to standardize the definition of global complexity for everyone.
Okay, so we have the reasoning model and we have the global fuel for it. When you build something this complex, how do you even test it? You can't just drive 100 million miles every time you tweak the model.
You can't. And that brings us to pillar 3, the testing environment, Alpasim. Because as these models get so complex, traditional open-loop evaluation just isn't good enough anymore.
Just remind us, the problem with open-loop testing is?
So open-loop means you feed the model a snapshot of data, it predicts an action, and you check if that action was theoretically correct. But it never sees the consequence.
Right. There's no feedback.
No feedback. Closed-loop testing is necessary because the car's decision actually affects the simulated world, and the system has to react to its own actions. It lets a model feel the consequences.
And Alpasim is the open source framework for this kind of high-fidelity, closed-loop testing at a huge scale. What's the big technical innovation that lets it scale so well?
It's the microservice architecture, which allows for something called pipeline parallelism.
Okay.
So in a traditional simulation, it's sequential. The driver module decides, then the physics engine calculates, then the renderer draws the new scene. It's slow.
A huge bottleneck.
A massive bottleneck. Alpasim breaks that. It has separate microservices, driver, renderer, physics, all running in parallel.
So while one scene is rendering,
the driver is already running inference for the next scene and the physics engine for the scene after that. You're overlapping all the compute tasks, which dramatically boosts your GPU utilization and your overall throughput. It's how you can actually test a global model like this without waiting years.
And then this is already being used. I saw that it's integrated into the Sim2Val framework. What did that prove about the simulation's realism?
It proved that Alpasim is a genuine proxy for the real world. The framework showed that using it could reduce the variance between simulated metrics and real-world fleet metrics by up to 83%.
That's huge.
It is. It means developers can assess changes way faster and rely less on expensive, slow, real-world test miles.
Okay, so we have the 3 pillars: the reasoning of VLA model, the massive open data set, and the parallel closed-loop simulator. This is a complete toolchain. So what does it all mean? Why is a company known for selling hardware, making all of this, the software, the data open source?
And that is probably the biggest strategic move of all. It's a classic platform play, a very sophisticated sell-the-shovel strategy.
Right.
Their stated goal is to accelerate the autonomy middle class. That's the established OEMs, the Tier 1 suppliers, the startups who don't have a $10 billion R&D budget like a Waymo or the vertical integration of a Tesla.
They want to be the default operating system, the Android of autonomous vehicles.
That's the perfect analogy. By providing the open model, the simulator, the dataset, they just lower the barrier to entry for L4 development. And they hook the entire ecosystem onto their platform, which, of course, runs best on their proprietary hardware.
What does that do to the competitive landscape? Does this put more pressure on the big guys like Tesla and Waymo?
It absolutely does, but in a really subtle way. I mean, Tesla and Waymo have their own massive data moats, but open tooling standardizes benchmarks. It makes it easier for competitors to catch up because they're all working in a standard auditable framework.
And the audible part is key for regulators.
It's critical. That emphasis on reasoning, traces, directly addresses what regulators are going to demand. It forces the whole industry toward transparency, which is a standard that a closed proprietary system might actually struggle to meet. It gives the open ecosystem a regulatory advantage.
And this isn't just theory anymore. We have a confirmed near-term deployment.
Yes, this is the moment it becomes tangible. The first confirmed deployment using the NVIDIA AV stack with these Alpamayo reasoning capabilities will be in the Mercedes-Benz CLA platform.
And that's slated for Q1 2026 in the U.S.
That's it. And that's not just a product launch. It's a direct challenge to the internal autonomy programs at every major OEM in the world. It proves that reasoning-based driving is moving from the lab to the showroom fast.
Wow. Okay, that really puts the whole deep dive into context. So to recap this massive shift for everyone listening, we looked at the three pillars of the Alpamayo ecosystem. First, the Alpamayo 1 VLA model, which brings chain-of-thought reasoning and auditable traces.
Second, the physical AI datasets, with over 1,700 hours of global data to solve the long tail.
And third, the Alpasims simulator using pipeline parallelism for scalable closed-loop testing. All of it aimed at standardizing level 4 autonomy for everyone.
Exactly. And that standardization brings us to the final, really provocative thought for you to consider. Alpamayo is just one part of NVIDIA's much bigger physical AI vision.
Yeah.
You have other foundation models like Cosmos for world simulation and GR0T for humanoid robots.
Right.
The implication is that autonomous driving it's rapidly stopping being treated as this unique, isolated field.
Instead, it's just the first large-scale, high-stakes application of a universal reasoning-based AI for any machine that has to operate in the physical world.
Precisely. So if all these different systems, robotaxis, industrial robots, humanoid agents, are all being trained on the same open toolchain using the same reasoning architecture, what happens when they start exchanging knowledge about how the physical world works? Autonomy today is about a car. Tomorrow, it might be about the emergence of general physical intelligence. And the car was just the starting line.